presentation. So at the end, we give a couple of 10, 20 minutes for questions. But I can handle here in the background any question or any comments about the presentation. And so that's no problem. I think we can start. Gladson, assim que você achar que pode começar, você me dá um toque. Pode começar? Então, eu vou fazer a apresentação do professor Jozef em inglês, né, por conta do idioma do convidado. Good morning, everyone. On the behalf of the Material Science Graduate Program at the Federal University of Western Bahia, I'm delighted to welcome Professor Jozef Strečka from Pavol Jozef Šafárik University at Slovakia. And Jozef has his PhD from the Pavol Jozef Šafárik University. He will speak today on quantum entanglement in Heisenberg spin systems in a nutshell. Thank you very much, Jozef, for your availability. It's an honor to our graduate program to receive you as a speaker today. Professor Jozef is very close to Brazil. He had the opportunity to be here as visiting professor 2 times, right? The Federal University of Lavras, Minas Gerais, Federal University of Alagoas. And Professor Jozef also has a strong collaboration here in Brazil with Professor Marcelo Lira in Federal University of Alagoas. So Jozef has an opportunity to be here in Brazil several times. So it's almost one of us, almost a Brazilian, right?
Yeah, I was more in Brazil than in Czech Republic, what is our neighboring country, you know.
Yes. So it's a pleasure to have you here today, Professor. It's an honor. Thank you for your availability. And now it's my honor to hand you over the virtual stage to Professor Jozef. Thank you very much. You can start your presentation.
Thank you very much for kind introduction. So before I'm starting, let me thank Clepson for the invitation to give a seminar at your university. It's really great pleasure. And I really like Brazil. I was probably 8 or 9 times in Brazil. I really was not visiting, let's say, Czech Republic so much. What is our neighboring country than Brazil. So it is always my great pleasure to collaborate and to speak with my Brazilian colleagues and friends. So in my presentation today, I would like to speak about quantum entanglement. I will start to go relatively slowly to some basic stuff from quantum physics, what we know. And then later on, I would like to specifically mention some very specific aspect of entanglement in Heisenberg spin system, which are in fact theoretical models of some quantum magnetic materials. So that's why it's like in a nutshell, because in the title, I will really like to cover and starting from very early basis up to what quantum entanglement is, what entanglement is not, and later on to some more advanced topics, how to measure the strength of the entanglement. So since I do not see you, so I propose that either if you will write to chat window some question during my presentation, Clepson, please just don't hesitate to interrupt me and read the question, or you can just unmute your microphone and just ask me, because I really don't have any response from my screen. So here is the outline of the presentation. So I would like to make some brief introduction to the quantum physics, maybe just to remind you about some basic terms which we know from quantum mechanics. Then I would like to say about some myths, facts, and open question related to the quantum entanglement. Always is a question, entanglement is a really interesting phenomenon, but the question is how to quantify it. So I will specifically focus on one measure of the entanglement. Of course, this is not the only one existing, but I think this measure, and the quantity is called negativity, is like really one of the most simplest measures of entanglement, and I will try to explain you why it's very simple. Then I will also mention some experimental motivation. I'm theoretician, but I am always trying to do research somehow closely related to some real-world systems. So you will see some experimental motivation, and then the case studies of two, probably the simplest Heisenberg dimers, including some theory, how to make the calculation. But the main part should be discussion of the most interesting results, because you will see that we will be able, after a relatively simple calculation, to break some myths in quantum theory, maybe some future proposal for experimental verifications, because that all will be only theory. And now there at the end should appear some question, okay, and how we can verify it by experiment? And finally, I will conclude with some summary and future probably outlooks, what can be. And I will also mention few papers of other groups, what I'm personally considering like very interesting. So maybe let me start with this slide. Current problems in quantum physics. So definitely quantum physics is nowadays one of the most intensively studied areas of physics at all. The reason for that is a realization or attempt to build quantum computers and to realize on these quantum computers and quantum computations. What a quantum computer is? You see over there some definition that it is some computational device which can make direct use of quantum mechanical phenomena, quantum superposition or quantum entanglement, to perform some logical operation with the data. So you see that there are two maybe special words which I will return later, quantum superposition and quantum entanglement. What's the difference between both of them and why it's interesting? So one thing in the European Union is always say that priorities in research are given by the Commission of European Union, and few years ago, I think it was in 2018, if I remember right, or 17 or 18, European Union Commission announced quantum flagship program when they gave 1 billion of euro for 10 years. So nowadays it is the best financed research in all Europe, and really there is a big attempt to make some progress in this field. We see that really without quantum superposition or entanglement, we would not be able to use this interesting property of quantum physics. So we can ask the question, what is in fact this quantum entanglement? How we can characterize, define, and quantify it? How we can detect quantum entanglement either theoretically or experimentally? And then all these questions I will try to address, and more specifically, since I am long-term working in the field of magnetism, how to study all these phenomena in some quantum magnetic systems. I'm sorry not to speaking so much about quantum computers. Definitely, it would deserve its own presentations, but let me focus only one of possible realization of quantum computers. I will not tell you nothing about this superconducting base quantum computers or optical traps or I don't know, some in semiconductor based quantum computers. That would deserve really very, very different presentation. So let me remind you all the basics, what I probably expect that you know from elementary course on quantum physics. So one of the basic principles of quantum mechanics is so-called superposition principle, which tell us that if some quantum system can be found in some state, and the state is always represented by mathematically by some state vector, and let's assign to some different state, let's say state vector ket phi j, what is in the first equation. And are you able to see when I'm pointing with the cursor on the screen or not?
Yes, we can see you.
Okay, so you see here is ket phi j. That means that this is jth state of some quantum mechanical system. And what the superposition principle says, that if quantum mechanical system can be in more states, let's say n, then it can be in any linear combination of them. So what tells us first equation. What is also very important, there is a postulate about eigenvalues and eigenvectors. So we can assign to each physical observable quantity some operator. And what is very important, to find some eigenvectors. What does it mean? If you apply this operator on some state vector, you will not change it, or only you will multiply it by some constant. And this constant is called eigenvalue. And this eigenvalue is in fact what you would measure for the respective physical quantity if the given physical system is in the state described by the eigenvector, so by this state vector. Of course, what is not so nice property of quantum physics is that the measurement is probabilistic. So if you decide that you want to make measurement of some observable represented by some operator, outcome can be very different. So it can be one out of this n state vector, and it is not only that this is random, but these random outcomes are weighted. So some of the outcome measurement can appear with high probability, some with lower probability. And that's the physical meaning of all these coefficients, Cj, in quantum superposition, because square of absolute value gives, in fact, probability of measuring. So let's say C1 square in absolute value, that's the probability of measuring the first eigenvalue for a given operator. That's why many times it doesn't have meaning to speak about individual outcome of the measurement, and we can say only about the mean values. So mean values in quantum physics are defined by such kind of inner product between so-called bra state vector and the final outcome of action of operator on ket state vector. So this is how we write it formally. In fact, this is not so useful formula, and much better formula is if you rewrite this formula in terms of so-called density operator. What density operator is, you will see it on the next slide, but you see that the mean value for some physical quantity, for some observable, you can simply get as a trace of the product of density operator and given operator. So under the operator, you can imagine always some square matrices. So what is here after the trace is in fact product of two square matrices, and you don't need to find all the elements. You only need to sum up the only elements appearing on the main diagonal, and then you will be able to get the mean value. This is especially useful because you will see that we have to distinguish between pure and mixed state, and while the former formula works only for pure state, this more general formula is of general validity and works both for pure as well as mixed state. So So here is probably how one can reach why it should be defined like that. So if you look for the first formula, that's only repetition from the previous slide. So it is principle of superposition when the general state vector of some physical system can be written in terms of linear combination of some basis state vectors. And how to get this brass, you see that what we have done only complex conjugation. So that means this asterisk on the top. And then we can just elaborate this mean value. First, let's apply operator on the original state and use one of the very important properties. There are two properties of any operator. Operator must be linear and Hermitian. So we will use the first property, that this operator is linear, so it doesn't act on these complex coefficients, and it only acts on the relevant state vectors. And what then next? Then we can perform this inner product with brass state vectors. That's why we have double sum. And now you see that the mean value is in fact equivalent to the product, and product of first two terms depends on two indices, I and j. So why not to write this in terms of one quantity, which we called rho, and with the two subscript j and I, and its definition will be exactly this one. And then why we can do that? You see that also this inner product, which is related to the operator A, it also depends on the state of two vectors, I and j, and that's why we can all assign them two indices. And if we do that, that in mathematics is nothing else like product of two matrices. So in principle, Aij, it's one element of some square matrix which is defined like that, and rho ji, and just notice that I changed the order of the indices. Formally, it should be ij, not ji, but if I want to use the property of the product of two square matrices, I have to interchange these indices. So this is the only exception in quantum mechanics that the elements of density operator are defined in a reverse order. Otherwise, everywhere where it's complex conjugation should determine the first index, and where is not complex conjugation should be second index, exactly as it is in this square matrix Aij. You see, here is this complex conjugation, because here I make complex conjugation of ket vector. And then you really need to perform the product of two square matrices and just summing up all the main diagonals. And that's why we can end up with this simple formula. Why I spent a relatively long time with explanation of such kind of trivial thing. Now, one can understand one thing. In principle, I can take here any physical quantity, any observable, and I see that for calculation of the mean value, I need the operator rho. That's why this operator is central in all quantum physics, and I think that's the most important operator among all, because it can, if you know it, in principle, you can calculate mean values of any quantity. This operator is sometimes called also state operator, and its matrix representation we know under the name density matrix. So that's all equivalent. What are the properties of this operator? First property is that it's Hermitian. You see that the mutually transposed elements, let's say 1, 2, 2, 1, are complex conjugate with respect to each other. That this kind of matrices in mathematics we call Hermitian. Why it's very important? Because then we know that all eigenvalues of these operators are real. if you look what is on the main diagonal, it is square of absolute value of given probability amplitudes, and we only told that's in fact the probability of a given state. So let's say in this state vector, Cj determines probability amplitude of the state vector ket phi j. That means that Cj square is in fact probability with which we found a given state. And it can be shown that one can have a look on it like on one column vector. So we can order these probability amplitudes in the form of one column vector. And then bra, state vector, we need to make complex conjugation. But since we also want to define some product between bra and ket state vectors, so we will not only make complex conjugation, but also operation of transposition. So it will be one row vector. And why it's interesting? Because then if you multiply this one column and one row vectors, but not in the form of inner product, but in the form of outer product, what does it mean? We will take the whole row and multiply by C1 complex conjugate. We are getting first column of this operator, right? If you multiply with C2 complex conjugate, the second, and that means that the density operator formally can be written like outer product between ket and bra state vectors. And what we know about this outer product, it is so-called projection operator between state vectors usually are satisfying orthogonality conditions. So if they are orthogonal with respect to each other, some two vectors, such kind of product or mean value with the density operator would be zero. So that's why we say projection operator, because it only tells us how one vector, whether it's independent or is somehow dependent on some other vector if we perform, let's say, inner product with the density operator. Okay, so now we can end up with the definition, namely, if the state can be described by density operator, which can be defined like inner product of only one state vector, we will call this that it is a pure state. So it is in fact definition, and that's why it was really necessary to go all through that, because I just make definition of all pure state. Pure state are those which can be described by a single state vector and state operator in this form. And mixed states are not so nice definition. Why? Because it's negative. So mixed states will be then the state which cannot be described by the state vector and the state operator like that. So the question then is how they can be described. So we should forget about state vector, because it is not possible to find only single state vector or characterize mixed state through the single state vector, but we can still find density operator for mixed state. And how it will look like, it will be some weighted sum of density operators of some pure state, while all these weights pk are positive, and they define the probability of a given state, and we are just simply summing them. So of course sum of all probabilities should be equal to unity, so we have to have our quantum system in one of the state with 100% probability. Okay, so if we introduce all these basic notions, we can come to the word which I mentioned, and which will be probably key word of my presentation, what is entanglement. So let me briefly mention history of this word. So the first mention of the entanglement, in fact, comes from Schrödinger, but the principles why this term was introduced to quantum physics goes back to the very seminal paper written by Einstein, Podolsky, Rosen about some very strange paradox, which is called EPR paradox. What EPR paradox tells, or what these three guys told, they assume that any reasonable physical theory should satisfy locality principle. What does it mean? If you perform measurement on one physical system, that physical measurement should not have instantaneous effect upon another spatially separated physical system. Why it should be like that? Because due to Einstein, no influence can travel faster than speed of light, so that's why should not be instantaneous. And right now you will see that we will have some problem. So let's consider, let's say, one pion. It's very unstable particles, which decays very fast, and it can decay into the electron and positron. Pion is electrically neutral particle, so sum of charges is zero. Before decay, after decay, everything is fine. But what is problematic is that pion is without intrinsic angular momentum. So what does it mean? We say it in one word, spin is zero. But the electron and positrons are spin 1/2 particle. So if you try to measure spin of spin 1/2 particle, you will find them either h bar over 2 or minus h bar over 2. And those two states can be represented either by spin up or spin down state vector. So that's only our simple notation. What does it mean? It means that before measurements, angular momentum was zero. So also after measurement, angular momentum should be also zero. And we know from the experiment that we have two possible cases. Either we will find electron with spin up, then positron will be with spin down, or vice versa. But now we face serious problem. Just imagine that the electron moves to the left 500 meters, positron to the right 500 meters. So they are 1 kilometer far apart. And in the case that you will measure spin of electron, you will immediately know spin of positron. And that would not be strange, except that whether you will find an electron with spin up or down is completely random. So it is not defined somehow previously. And now we really violate locality principle, because if we say that something we don't know, because outcome of measurements probably it's random only because of our incomplete knowledge about the physical system, and maybe it's determinable, but or the second option is that the quantum mechanics is completely wrong, because in quantum mechanics we spoke only about probabilities of measurements, right? And from that point of view, this is what is called EPR paradox. So if we don't want to get rid of probabilistic nature of quantum physics, then we are violating locality principle. And this is what Einstein, he was still not call it entanglement, but Einstein called it spooky action at a distance, because really measurement on two spatially separated quantum subsystems instantaneously influence each other. That's property we called entanglement. So entanglement was posed by Schrödinger, and in fact doesn't make any problem if you don't ask from some physical theory to satisfy locality principle. If you would ask me the question, okay, but how it's that? How positron will know that if the outcome of measurement on electron is random and I will just make it, and I will find it that it is in spin down, how positron will immediately know that its spin has to be up with infinitely large speed, not greater speed than speed of light, but with infinitely large speed. Explanation, which might be current explanation, and already dating back to the years when Schrödinger was fighting with Einstein about this term, is very simple. You should not look on electron and positron like two separate objects. They have common history. They appeared from the decay of pion, and there is something subtle in between them which makes them not independent. So if you perform measurement on one subsystem which is connected to the another one with nothing what you can see by the eye, so of course you influence also the second subsystem. So once we have pair of particles with this property, then we say about entanglement. So this is the basic principle of entanglement. But one should say that this is very fragile phenomenon, and if you will do it in air, an electron and positron will be moving 500 meters to the left and 500 meters to the right in some air, which is containing nitrogen and oxygen molecules. The entanglement would disappear very fast due to collision with other stuff, with molecules, with the light, whatever is there, and this fact is called decoherence. So it's always a problem that we always have decoherence, and that's not so easy to get rid of them. Okay, so now we can say some definition. What is entanglement? Entanglement is then physical phenomenon which occurs if state of some particle, of many particle subsystem, cannot be described independently of state of other particles. So it can be bipartite entanglement, let's say like those two guys which are shown here, or if this entanglement is connected to more particles, it can be multipartite entanglement. And you can find this phenomenon in nature, in quantum materials, quite a lot of types of quantum materials of very big diversity. Why the entanglement is interesting? Because subsystems which are entangled are subject to stronger correlation than allowed by classical physics. So this is a reason why we have to investigate entanglement. It can lead to some new quantum technologies, to quantum computation, quantum information processing, communication, teleportation. So there are a lot of other consequences why quantum entanglement could be very interesting. And why, if I will speak mostly about quantum spin system, why those should be interesting? Because it was shown, for instance, in this chemical science paper, that quantum spin systems are really promising solid-state resources for encoding quantum bit, so elementary logical unit of information, which we called in one word qubit. So it's always, right now, it's big search for searching some platform of realization of qubits. One word should be said about the difference of quantum superposition and quantum entanglement. So let me first speak something about zero temperature, because at zero temperature, you can characterize the system using the state vector. So if we speak about quantum superposition, so we can say that, for instance, this state, which is shown on the left, ket F, is more simple. It's a little bit strange with respect to ket S state, which looks at the first sight like to be more simpler. But simpler is ket F. Why? Because if you look on this state vector, so in the second line, by proof of principle, you can very easily prove that if you will perform this tensor product between those state vectors of first and second particle, you will end up with this quantum superposition. So this kind of special state, which can be separated into the form of tensor product of state vector of individual subsystem, we called they are separable, and they do not possess any entanglement. So they are without entanglement. They are, of course, in quantum superposition. You know that second power of this absolute value of this number gives the probability of a given state. So all four states appear in the final state with 25% probability. So from that point of view, it's quite clear. Here, both states appear with 50% probability. So from that point of view, it might look at the first slide as simpler state because we have only superposition of two basis state vectors, not four. But if you will try to perform this separation into two linear combination of individual subsystems, you will never get the final result. So why it is like that? Because once you have spin up for up spin and spin down for the first spin and spin down for the first spin, so the coefficient A and B must be non-zero. But in that case, if for the first case you need to have non-zero value for the spin down state, so that means coefficient D. But if you have non-zero coefficient D, non-zero coefficient B, so you need to have down-down state in order to be separable. Since we don't have it here, it must be entangled. So it's very simple proof that this state cannot be separated, and the pure state is separable if and only if it can be factorized into product of two pure states of both subsystems. And again, we have negative definition. If it cannot be factorized, we say that the state, pure state, is then entangled. So it's very easy, in fact, mostly it's very easy to find out whether pure state is separable or not. More complicated way how to find out is to perform Schmidt decomposition. I will not speak so much about it. But more interesting case are for us mixed state. Why? Because pure state are really true states only at absolute zero temperature. There is no physical system which would exist at absolute zero temperature because we cannot reach it. So all our physical systems are in fact in mixed state. And what we know, that's why I'm returning back to my very early beginning of my presentation, where density of operator of mixed state was this kind of sum, weighted sum with some positive numbers, pk, which are giving probabilities for these pure state density operators of some individual state in which the composed system can be. Mostly, the probability can be found, let's say, in canonical ensemble, that is 1 over partition function, and it depends on the Boltzmann weight, where is exponential minus beta times energy of a given state. Beta is inverse value of product of Boltzmann constant and absolute temperature. So this is how density operator of mixed state look like. So we have here this projection operator for individual state, and each of them is weighted by given probability, and we need to sum up over all possible states in the spectrum. Again, if you want to say whether a system is entangled or not, but at the level of mixed state, you can either perform Schmidt decomposition, or you can say whether you can make decomposition into subsystems. If you are not able to do that, in that case, we say that this density operator of mixed state corresponds to the entangled mixed state. If you succeed in separating, in that case, it will be only superposed state, but without entanglement. But definitely, this is not so easy task, and that's much more tricky. In fact, I really hate to perform Schmidt decomposition. It's very awful mathematical task. So that's why let's have a look for alternative procedure. So alternative procedure is to define some quantity. This quantity will be called negativity, and this will be measure of entanglement, and this measure will work both for zero temperature as well as non-zero, so both for pure as well as mixed state. So let's have a look on density matrix, which corresponds to some physical system. So what you see here is density matrix with the individual elements, diagonal elements define probabilities, and what you can also do, you can perform transposition. What does it mean? Of diagonal elements in the row and columns to interchange. What is the basic property if you make diagonalization? All eigenvalues of the density operators must be real, and that holds also for transposed density matrix. So it is very basic property of these all Hermitian operators. But then you can understand one thing. If you have a composite system, it's really bad that we introduce only two subscript I and j. Why? Because this bra and ket state vector should both have two indices. Because we have composite system, so it has to contain at least two indices. Let's say A and B corresponds to the state of the first subsystem, and alpha and beta to the second subsystem. So this is nothing written else like density operator, but now we will have like the subscript, instead of two indices, four indices. The first two determine the state of bra, and the other two of ket state vectors. Now you understand one thing, that you can perform not only transposition, full transposition, but also partial transposition. What does it mean? You will not interchange all states of the initial and final state. You can do it vice versa, as I have done it here, but you can do it also at the level of subsystem. What does it mean? I will not change the state of the first subsystem. I will change the state of second. So this is this index T2, so transposition with respect to second subsystem. This kind of operator is like new one, and we call it partially transposed operator. And what is its basic property? Perez has shown that if there is no entanglement, this partially transposed density matrix has still property of density matrices. All the eigenvalues are real and positive. But if there is entanglement between these two subsystems, then there must exist at least one negative eigenvalue. What does it mean? This is a very simple idea, because we are just performing partial transposition, then diagonalize the corresponding partially transposed matrix, and if we found at least one eigenvalue, lambdas here, negative, then sum of absolute value of those negative eigenvalues of partially transposed density matrix is called negativity, and it will then serve as a measure of entanglement, as was later suggested by Vidal and Werner. So in fact, Perez and later Horodecký showed that if we want to have entanglement, we at least need to have one negative eigenvalue, and Horodecký, Perez only make some suggestion, and Horodecký have proved it like mathematical theorem that at least for the two qubits or qubit Q-trees, it is necessary and sufficient conditions. So we know definitely that it's like that, and that's why this sum of absolute values of negative eigenvalues of partially transposed density matrix is really perfect measure of entanglement. Okay, so that was like introduction to the entanglement and measures, and let me show how it works in practice. So here is the most simplest examples, or the simplest examples. So if we take two interacting spin 1/2 particles, represented by two spins, here is a scalar product. We call this Heisenberg model or Heisenberg dimer if we have only two particles, and then apply magnetic field. What does it mean? We need to find first the working basis. Each spin 1/2 particle has two states. So if we have two particles, it's 4 states in total: up, 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 down, down, up, down, down. And then just applying all these operators. Here are these Pauli spin matrices, which you probably know from the basic course, and to find matrix representation of the Hamiltonian. Obviously, it is non-diagonal matrix, but it is easy to diagonalize because the first and last diagonal elements are coupled with only zeros, so that they are already eigenvalues. And then you need to solve this quadratic equation with respect to this middle subsector of phi 2 on phi 3 states. If you do this job, it's very simple exercise for half an hour calculation. You find out all 4 eigenvalues and corresponding eigenvectors, which looks like that. And in principle, you are done, because once you know all eigenvalues and eigenvectors, you can simply elaborate density operator, because it's 1 over partition function and exponential from minus beta Hamiltonian. So if you know you can Hamiltonian, then you can use the eigenbasis here, and application of any function of operator on the eigenstate of a given operator gives you corresponding eigenvalue. So it is easy then to compute all components of the density operators. They explicitly look like that. And here is the sum of eigenvalues from the previous slide. So in principle, this is very simple exercise. And then this matrix, one can perform partial transposition. So what does it mean? If you perform partial transposition, the elements on the main diagonal doesn't move. Why? Because we are changing up state for up or down for down. So that means nothing happens. But of diagonal elements, you should be careful, because you see that, for instance, row 2, 3 connects the state up, down with down, up. So if I interchange only the second particle, so down for up, so it will be down, down, and this will be up, up. What does it mean? Up, up is first, and down, down is the last. So this element has to move to this corner. So you see that partial transposition just changes position of these off-diagonal elements, but still it's very easy to diagonalize, because we know that the sum of negative eigenvalues of this partial transpose density matrix defines negativity. And then it's very easy just to get all eigenvalues. So if you diagonalize this matrix, so it's quite clear that row 2, 2, row 3, 3 are eigenvalues. And again, you solve only one quadratic equation with respect to this. And that's another 2 eigenvalues, what you are getting from the solution of quadratic equation eigenvalue problem. And what you see, these 2 eigenvalues are real positive because they are on the main diagonal, and square root of this sum is again something what is positive. So lambda 3 also cannot be negative. So only lambda 4 can be negative. So if you invert the sign, that will define the negativity in spin 1/2 system. And you end up with a formula which you can investigate as a function of magnetic field, as a function of temperature. And here is typical plot. So what you can see, if the field is less than 1, then you start from 1/2. That's maximal value of negativity. That means you have fully entangled state. And with increasing temperature, you are decreasing entanglement. The greater is the field, the more faster is this decay of entanglement with temperature. If you are pretty close, you see it is very steep. I even do not catch 0.5 because I put some finite temperature. And if you are at 1, that's the coexistent state between this fully entangled singlet state, which is realized in this ground state, and this is a classical separable state up. So it's some weighted value, and then again it disappears. What is interesting, even if the field is greater, you must have zero entanglement at zero temperature, but with increasing temperature, you are exciting your system with some probability to this state, and that's why entanglement can grow, and finally it can disappear. And it always... Sorry?
I think something let open his microphone by accident.
Okay. So it will disappear at the same temperature. So now I will just run very quickly through the other technical details, but I will ask the following questions. Or I will first say something what usually people say that it holds. First, entanglement is generally suppressed by increasing temperature. Second statement, entanglement is generally suppressed by increasing magnetic field. And the third, entanglement is generally suppressed by increasing spin magnitude. And what you will see in a moment, this is definitely not always true. So that are only myths, and there are no true facts. So, but the questions are how we could stabilize entanglement to sufficiently high temperature, and how we can experimentally verify it. So here is experimental motivation. So here is a compound which contains one copper 2+ ion and one nickel 2+ ion. Copper is spin 1/2, nickel is spin 1 particle. So it's magnetic molecule which has only two spins, 1/2, 1, which are coupled by strong antiferromagnetic superexchange coupling of order 141 Kelvin. And here are G factors from the measurements. So that's some experimental paper from this paper by Professor Hagiwara, published in Journal Physical Society Japan long time ago. What I will show to you, how it will look like in theory. So one can perform some Heisenberg model. Of course, the basis will be bigger because spin 1 particle has spin 1, 0, and -1. That means it will be not 4x4, it will be 6x6 matrix. And one can perform all the other stuff. One can find density matrix. It can be still diagonalized. One can perform partial transposition. One can diagonalize all the eigenvalue and find the negativity. So I will not explain all the technical details. More or less the same like for the previous case. But let me show you the results because these are particularly interesting. So for instance, in the first case, if you are a low enough field, this is the lowest energy eigenstate. So you see that you have quantum superposition, definitely, between spin -1/2 +1 and 1/2 0 state vectors with some very special probability amplitudes which are given here. If you apply any non-zero field, you can end up with this definition of negativity calculated from this vector. And you see that there must be some entanglement between them. And also you see that it depends on the anisotropy term. Maybe I forgot to tell. Delta is exchange anisotropy here in the Heisenberg coupling. If it's unity, there is no exchange anisotropy. And D is single ion anisotropy, which acts only on nickel ion on spin 1 particles. Spin 1/2 are not influenced by single ion anisotropy. And you see that the negativity depends both on exchange anisotropy, single ion anisotropy, but also on magnetic field, provided that the G factors are different. And if you have two different magnetic ions, they must be always different. If you have high enough fields, you have ferromagnetic ground state, then negativity turns out calculated from the state vector very simply, 0. And now you can understand from this formula that the largest value of negativity 1/2 you can reach if d over j will be 1/2, because this unity and that will cancel, and g1 equals to g2, because also the field term cancel, and then square root of a times delta square, delta cancel, and square root of 2 divided by square root of 8 will give you 1/2. So this is schematic picture. Then spin 1/2 atom creates perfect singlet bond with one of the electrons of nickel ion, and the another one is polarized to the magnetic field. So nickel will behave like spin 1/2 polarized particle in that case. And that's the strongest entanglement which can be reached in this system. And indeed, if you study negativity as a function of the magnetic field, you see from infinitesimal field just make the increase, and then you achieve very high value and then goes down around the saturation field when you reach classical state. If you increase temperature, then these transitions become smoother. So what? And this is regardless of whether you consider negative or positive single anisotropy. So what I just showed on these two figures, entanglement can be substantially enhanced by magnetic field. We start from this value and then we are enhancing, and here is a really huge change. Why it's like that? Because ground state at zero field is twofold degenerate, but by magnetic field you split due to Zeeman splitting of energy level degeneracy, and pure state always have higher entanglement than the mixed state. So this is the reason for this unusual behavior and for the breaking up this myth. If you look for density plot of negativity in temperature magnetic field plane, then you can understand something else. So if you fix field higher than saturation field and then you increase temperature, then you see that you start from non-zero or from zero entanglement and then you acquire non-zero. So what does it mean? Entanglement can be invoked upon increasing of temperature. In this case, only if the field is greater than the saturation field, but I know also examples when it's not only for field above the saturation field. And again, it holds regardless of the type of the anisotropy. Here, one can see it maybe in a more clear way. And what I try to plot in these two panels, if we take into account all experimental data for the compound, then we can make some theoretical prediction about the entanglement. So we see that we can increase entanglement from roughly 1/3 almost to 1/47, and then the entanglement only very, very gently decays until it very abruptly vanishes at very high fields. So you see that the entanglement is quite robust against magnetic field of almost 140 Teslas. So what is unusually high fields. Here is a detail from this slope that the entanglement in fact is not constant. It slightly decreases with increasing the magnetic field. And here you also see how robust it is against the temperature. You see that the entanglement of this complex should disappear only at 150 kelvins. Now, if I will connect it to my beginning of my presentation, for instance, this quantum computers built on superconducting circuits require temperature below 1 Kelvin. Technologies based on magnetic materials would be much more stable, and that's why they are very interesting. And here is density plot again of negativity, which just delimitates entangled region from disentangled. So you see that you can keep entanglement up to very high temperature and very high fields. So of order, so even if I would say that at least 0.1 entanglement I need for some practical application, not 0.01. So I can keep up entanglement at least up to 115 kelvins in this compound. Of course, there are compounds which can keep up to much higher temperatures, but this is already very nice property, and the magnetic field is not violated. So let me go gradually to the conclusion. What I just tried to show to you is that the entanglement is generally suppressed with increasing temperature. This is not always true, so you should not trust this statement. And temperature may slightly enhance the entanglement, even if this is weak effect and mostly it appears above saturation field. More interesting is that the magnetic field may substantially enhance entanglement, and to the best of my knowledge, it happens only if the ground state is degenerate. So that means that you need to have degeneracy in zero field, and the field has to lift the degeneracy, and in that case, entanglement is not suppressed by increasing magnetic field. So also this statement is not correct. A last statement, I do not present it, but we make calculation for general case with mixed spin 1/2 and spin S, and find out analytical formula of threshold temperatures where entanglement disappears. And if you look for these values, you see that increasing with spin, we can increase thermal robustness against temperature. So entanglement is generally suppressed by increasing spin magnitude. This statement is partially correct and partially no. Why? Because trend of the entanglement is always suppressed, but its temperature resistance no. So if you increase spin value, you can entanglement can persist up to much higher temperatures. So good choice of constituent spin may optimize entanglement. So probably not to take very small value, which will maybe slightly lower the entanglement, but also not too high, because we will have better thermal robustness. But if the spin value would be too high, in that case, the entanglement will be very, very small. So really, there seems to be some optimal value. And how to verify it? Because all this, what I showed you, were based on theory. So all these entanglement measures are connected to density operator, and density operator can be re-expressed in terms of pair correlation functions. And in fact, from inelastic neutron scattering experiment, it's possible to get pair correlation function from the component of the structure factors. What does it mean? I don't have here results because they are more elaborate, but we are now working on how to connect all these entanglement measures to the component of the structure factors. So there are possible way of doing that. And maybe something only running through some notes. So I showed you only some magnetic molecules, which are the simplest quantum magnetic materials. You can extend all this calculation also to some more complex system. For instance, here on the picture, you see natural mineral with very strange name, pipit, found on Russian territory close to some volcano, Tobachnik. And these needles are in fact the realization of such kind of chains. And one can show this kind of double chain, which we call usually two-leg ladder or tetrahedral chains, are also possible to have very strong entanglement as shown in this figure. So here is how the real crystal structure looks like. How is this approximate structure? Another beautiful natural mineral, azurite. It has in the structure, we call it diamond chains. So if you look, this diamond chain schematically shown in upper part of my slide is corresponding to this chain-like structure of azurite found in this beautiful mineral. Again, you can see that the entanglement in azurite can persist up to 30 kelvins and pretty high field of 50 Tesla. So it has very nice window when the system is entangled, maybe less than what I showed you before, but still much better than, for instance, in superconductive transmuon qubits realized in superconducting circuits. And what you can also do with such kind of entanglement, Brazilian colleagues from Federal University of Louras has shown that it's possible to perform of quantum teleportation between two different diamond chains. So if you take two chains in azurite which are non-interacting, then you can teleport the states between two spins of two different chains to their neighbors, and the fidelity of teleportation, what is shown here, FA average fidelity, is at sufficiently low temperature. It can even achieve unity, what is 100%. This is the definition of the fidelity. How one can do that? It's more complicated protocol for teleportation. Again, it would require some separate presentation about that. But this is definitely one of very interesting features, maybe right now only theoretically predicted, but I think experiments are waiting for that. So most of my presentation was built on this Physical Review B paper from 2020, where we presented the most of the result. So if you want to have some more details to read about it, so just check out this reference. And thank you very much for your attention. Hopefully it was not too much. I don't speak too long, but if you have any question, and if I will know the answer, I will like to chat with you about this.
Thank you very much, Jozef. Thank you very much for the talk. Thank you very much for your ability to contribute to our graduate program. We now invite the audience. If someone would like to ask something, please can open your microphone or raise your hand here on the Google Meet platform. Let me check the YouTube channel. No questions there. Somebody has any questions, please. If anyone has a question, I have made some notes during the presentation. I could have some questions. Vonson is my PhD student, Jozef, I was talking about. He's attending the seminar too. He's working on that spin 1 quantum battery I talked about earlier. He's my PhD student. Anyone has a question, I can. If not, I can advance with my question. I take a couple of notes. Okay. First of all, thank you, Jozef, for your presentation. Enlightening talk.
You're welcome.
I have some question about the practical use of those systems for quantum computing today is kind of hard, because due to the superconducting devices, I find that the literature gives his attention to the superconducting device and forgets the application, a practical application of the systems, of those systems for quantum computing. There is some practical implementation for those systems. I never saw a practical use of those systems for quantum computing, in fact.
At least I know about two groups, experimental groups, which are making attempts in this direction. First group is from the Italian professor Dante Gatteschi and Roberta Sessoli, and the other one is from the French, from France. It's the group around Wolfgang Versdorfer. So let me briefly tell you what I know from the presentation which I attended at some conferences, and I have been able to see some presentation of those groups. So there is one big technical obstacle. What they usually try to do that they want to have some platform, some metallic polished plate, usually made of gold, and these magnetic molecules want to attach to this surface and work with the qubits. So first problem is that these magnetic molecules, it's very hard to attach, and then it's very hard to control them. So probably this is a reason why the technology is not so far like with these superconducting circuits, where this problem definitely doesn't appear, because you only need to perform Josephson junction to cool down to very low temperature and it works. So, but what I have seen on one of the presentation, they were able to deposit one of the magnetic molecules on gold polished surface, and just to show that the basic quantum computation they can perform in such a way that they use multi-sequence pulses, like in electron spin resonance, but with not one frequency, but multi-sequence pulses. And what they were able to show, first, that the system really is in entangled state up to relatively high temperature, so it keeps its property. So I know that it works. Also, they, instead of qubit, because the molecule has more complicated magnetic structure with higher spins, so they can realize not qubit, but qubit. And they say that this is really great because it offers much greater possibilities for performing quantum computation, because not only quantum computation is important, but the error, this quantum error corrections and is very important to reduce it. And they told that it's really performing the operation with qubits. You can use some states of the qubits to reduce this quantum error correction, and they found some error correction for that. And something similar was done also with Professor Wernsdorfer, who showed the practical application, and he showed another aspect. What I was really wondering, he showed that he achieved decoherence times of 1 millisecond. It was maybe 700 microseconds, if I remember right. But one could say, okay, 700 microseconds, one cannot do nothing, right? But one should say that operation time for one logical operation with these magnetic molecules is of order tens or hundreds of picoseconds. So that means that this window, time window, allows more than 1 million logical operation with single molecule. His molecule was very strange. It was like a wheel made of 7 chromium and 1 nickel ion, and in fact it was not a single molecule. There were 2 molecules bridged somehow, and he told that was the best performance what he was getting. So if you ask me about what I have seen on some conferences in Europe, this was probably for me like 2 most convincing evidences that these kind of quantum materials are really of some potential. Whether they will really go up to such a stage as superconducting quantum computers, I don't know, because I see a lot of really technological obstacles, but there is a chance to overcome all these.
Great, I would love to see those work. I never saw those results. I would love to see this work, because talking about these huge coherence times, that's important, because that's the exact approximation we do to perform quantum heat engine model, for instance, ensuring that during that specific thermodynamic process, the system will be in thermal equilibrium, so we can perform a thermodynamic cycle quasi-statically. So we have a quasi-static process, and we need to ensure that the times related to the implementation of the systems, the implementation of the process guarantees that the system will be in thermal equilibrium during the entire cycle, during the entire process. So that handling these coherence times is a matter of interest for the quantum thermodynamics area. So I would love to see those works. I will also search it.
Generally, most of the compound have coherence time of order microseconds or 10 of microseconds. So the people working in this area really are hunting for molecules which have as high as possible decoherence time. And currently, world record is probably of order 700 microseconds. What is already very, very nice time scale for performing quantum computing.
Yes, I saw those papers from Moreno Pineda, from Panama,
that's also
Coronado. Yes,
yeah.
That's
great. From Spain, but also there is a competing group of Wolfgang Versdorfer. That's also.
Yes. Someone has some question? If someone has some question, please open your microphone. I'll talk in Portuguese now. Se alguém tiver alguma pergunta, pode falar, colocar no chat em português mesmo, não precisa ficar receoso também não. Pode até abrir o microfone e falar em português também, caso alguém tenha alguma pergunta. We have space for one more question. Time for the people to open this microphone. No? If not, I have my last question. Okay, Lucas. Lucas said that no doubts, no questions. Elias, a professor of program, just say thank you. Okay. I have one question, one final question, Jozef. When you talk about, there's two questions in one. That increasement in the entanglement with the temperature, that increasement of the entanglement at the temperature to low temperatures is related to the level crossing, right? To the quantum level crossing, and it leads the systems to a state with a higher degree of entanglement. That's why we see those increasement at the temperature. So that quantum level crossing is particularly interesting for us because we saw recently that level crossing that increases the entanglement at the temperature can lead to the high efficiency of a quantum heat engine. So, for instance, the Carnot, if we can reach the Carnot efficiency from a quantum heat engine around operating using our quantum engine to operate around those quantum level crossings. So that enhancement of the entanglement will be directly associated with an enhancement of the efficiency of a quantum heat engine. I'm sorry. That increasement of the temperature is related to the increasement of the efficiency in the quantum heat engine. So it's very interesting for the quantum thermodynamics area. But I'm sorry, I'm very sick those days. But my question is related to the negativity. I'm sorry. I'm sorry. When you calculate the negativity using the partial transposition, that partial transposition do not alter the quantum coherence of this matrix, right? I never think about it. This has some consequences for all the other quantum correlations. I never thinking about it because the partial transposition will not change the quantum coherency of the density matrix. This partial transposition can be applied for some processing those materials or quantum process that could use this invariance of the coherence through partial transposition. Have you ever saw something in the literature exploring this invariance?
Okay, so maybe I will not give you very satisfactory answer to this. I haven't seen nothing like that. From my point of view, it's only mathematical trick which is very useful, but I wouldn't tell that partial transposition is some reality what you can easily somehow implement in some real world system, because partial transposition in fact means that you need to interchange the states of one subsystem while keeping the another one fixed. And that I couldn't imagine how to do in practical application, because if you want to perform some local change, you usually also change the second subsystem. So I'm not sure whether maybe in the future it would be possible with some local probes to change the state of the one subsystem. But if it's entangled, I feel that the change of the state of one of the entangled particle will instantaneously influence the second one. So I don't think that it can be practically implemented so easily. Maybe it is even not possible at all. So from that point of view, I am just taking it more or less like mathematical routine, which is very useful for calculation, for introducing measure of entanglement negativity, but probably it has nothing to do with some physical reality that you want to really perform something on some real world system, I would say. And for the first question about this increase of entanglement, yes, in principle, it is always connected somehow to the crossing, but the most interesting are those states which in fact are degenerate at zero field. So in fact, they're crossing at zero field, but probably nobody is showing them going to the negative field. And in that case, really, always it happens that if you even take infinitesimally small field, you can achieve a very huge increase of entanglement. Of course, crossing can be also at the non-zero fields, but then whether entanglement will rise or decrease will depend whether the state appearing at a higher field is more or less entangled. And from that point of view, mostly, I don't say, I have seen some counter example, but mostly the state at higher fields spins at higher fields are more aligned to the magnetic field, and that's why they usually possess a lower entanglement. So crossing at finite fields, I would say that increase of entanglement can happen, but it's much more rare.
Tá mutado, Cleps.
Oh, sorry. Sorry. Thank you very much, Jozef. Thank you very much. I would like to extend our thanks from our graduate program for your enlightenment talk. Thank you very much for the availability to contribute with our graduate program. And I'm closing the seminar. So, eu estou em português. Gladson, acho que pode encerrar lá a transmissão.
Okay.
Thank you very much, Jozef.
From my side.
Thank you very much. You are welcome here in our university. You have the opportunity. In fact, you will come to the Brazilian Material Research Science meeting this year.
When it's meeting?
It's in the end of October, if I'm not wrong. The end of October, the Brazilian Science Research meeting.
I didn't know about the meeting, so I do not register it yet, but maybe I can still check out because I still have some travel money. But
I think the registration is ended. I think the registration has ended last month or something like that.
Okay.